This conference will now be recorded.
Yeah, let us see. In the last class, we discussed the properties like area under G of t and area under G of f. And we have seen an example also for the area under G of t as well as area under G of f. Now, in today's class, I am going to discuss about the differentiation in time domain. Please first try to understand this. Now, as you know, you may ask, what is the use of this differentiation property? First, try to understand. We have a relation. We have seen in the first unit, we have seen various waveforms like triangular waveform, rectangular waveform, impulse signal. Like that, we have seen different waveforms, different signals also. Now, if I ask you to find the Fourier transform of an impulse, you can find it. But you can find that using differentiation property also in a very easiest way. We'll see how these properties will help us and how to solve this in detail in this property. Now let us see, uh, when you see that this differentiation in time domain, please try to understand. That means you are considering a time domain signal and you are applying the differentiation in time domain. So which means that it is nothing but d by dt of g of t. Now, let us see. We know the Fourier transform of g of t is g of f, and the inverse Fourier transform of g of f is g of t. Then assume that the first derivative of g of t is Fourier transformable. Please try to understand. So when you differentiate the g of t, which is g dash of t, which you know, if the first derivative is also Fourier transformable, then you can use this property d by dt of g of t, which is equal to j2 pi f. The Fourier transform of d by dt of g of t is j2 pi f into g of f, or the inverse Fourier transform of j2 pi f into g of f is d by dt of g of f. Now please try to understand. Now here you are going to get g of t, and for g of t you are applying that time differentiation. So to get this g of t, first you need to start with inverse Fourier transform. Keep this point in mind. So when you write the inverse Fourier transform of g of f, which you can write as g of t, which is equal to integral minus infinity to plus infinity g of f into e power j2 pi f t df. Now please try to understand. You are finding the inverse Fourier transform of g of f, which is nothing but g of t. Now what we have to do is, you are applying the time differentiation to g of t. So this is g of t. Now you apply time differentiation on both sides. When you apply time differentiation on both sides, I can write it like this: d by dt of g of t equal to d by dt of this right side term, which is integral minus infinity to plus infinity g of f into e power j2 by f t dt df. Now first you apply, as we have the differentiation with respect to time domain and we have integration in frequency domain. So this g of f will not have any effect on this term. So you keep this aside, but if you observe this exponential term, and this will have an effect. This will have an effect. So you please try to understand how you have to use this. It's a simple technique. You need to, when you have differentiation, you need to apply d by dt of uv. So when you differentiate it, u into derivative of v plus v into derivative of u, from that, when it is in frequency domain, when you differentiate it, it becomes 0. So that you will not get that. So when you differentiate it, so this exponential term, I can write it as, since you are differentiating with respect to time, so I can write this e power j2 pi of t as j2 pi f into e power j2 pi ft. And when you rearrange this I can write it as the inverse Fourier transform of g of f. The inverse Fourier transform of g of f is nothing but g of t, which you know. So this you can write it as g of f. So now please try to understand. Now you take this f inverse to the other side. When you take this f inverse to the other side, since you are having d by dt of g of t, since when you have f inverse to the other side, it becomes f of d by dt of g of t, which is j2 pi f into g of f. This is how you will get this differentiation in time domain. So as I did this differentiation only once, I'll get d by dt of g of t j2 pi f into g of f. Suppose, as we know, we can go for differentiation of nth order in general. So which I can write it as d power n by dt power n into g of f, g of t, which you can write it as j2 pi f whole to the power of n into g of f. So that means if you differentiate it once again, then you will get d square by dt square. Like that, you go on doing that. As we have exponential term, e power j theta, you can write it as j e power j theta. So finally, you'll get so many terms like that, which is to the power of n. That is how you can do this differentiation in time domain. Is this proof clear to all of you? Please post it in the chat box. Otherwise, I am going to repeat it once again. Please post it in the chat box. Is this differentiation in time domain is clear to all of you or not? Please post it in the chat box. Differentiation in time domain ప్రాపర్టీ క్లియర్ గా అర్థమైందా లేదమ్మా? ఒకసారి చాట్ బాక్స్ లో పోస్ట్ చేయండి అమ్మా. Or shall I repeat it once again? చాట్ బాక్స్ లో పోస్ట్ చేయండి అమ్మా. డిఫరెన్షియేషన్ ఇన్ టైం డొమైన్ అర్థమైందో లేదో? నేను అడుగుతున్న క్వశ్చన్ ఒకసారి వినండి. డిఫరెన్షియేషన్ ఇన్ టైం డొమైన్ అర్థమైందో లేదో ఒకసారి చాట్ బాక్స్ లో పోస్ట్ చేయండి. Is it clear or shall I repeat it again? ఎవరైనా అన్మ్యూట్ చేసి మాట్లాడటం కానీ లేకపోతే చాట్ బాక్స్ లో మెసేజ్ పెట్టడం కానీ చేయండి అమ్మా. యా ఉపనయ యా see okay, let me use this I'm minimizing this. Now I'm using this Jamboard to explain this. Let us see this. Now let us see. All of you, please see here. I am going to prove it for your understanding purpose. Just see. As you know, the Fourier transform of g of t is g of f, and if I take this Fourier transform to the other side, then it becomes inverse Fourier transform, which you already know. I'm going to write that also. The inverse Fourier transform of g of f is g of t. Then if we see this, if we assume that if g of t is a time domain signal, then if I apply the time differentiation to this g of t, which I can write d by dt of g of t, and if I assume that whatever g of t that is given to us, you can find its Fourier transform, and if we differentiate that g of t, that is also Fourier transformable, Then I can write the Fourier transform of d by dt of g of t, which is j 2 pi f into g of f. This is what this differentiation in time domain properties. Now please try to understand. You are going to get a time domain signal you need to consider, and you need to differentiate that time domain signal, and you need to apply Fourier transform to that. Now please try to understand. To get this g of t, first you need to start with inverse Fourier transform. We know the inverse Fourier transform of g of f, which you can write the inverse Fourier transform of g of f, which you can write it as g of t, which is equal to integral minus infinity to plus infinity capital G of f e power j 2 pi f t df. Since you are applying this, you have a function which is in frequency domain, so that you need to do the integration also in frequency domain. So now, since I have the other right side term which is g of t, so I am going to apply differentiate. I am going to apply differentiation on with respect to 2 and t on both sides. So I can write dwrt. I think you know, differentiate with respect to t on both sides. Then you can write d by dt of g of t. I'm not going to write. I'm going to consider g of t. I'm not considering this. So which is nothing but the inverse Fourier transform of g of f. Just for this, since you need to apply differentiation in time domain, so I'm considering g of t, which is equal to d by dt of, just I'm applying differentiation on both sides. Integral minus infinity to plus infinity g of f e power j 2 pi f t df. Now please try to understand. Don't disturb the left side term. Keep that left side term as it is. Now check the right side term. Now if you observe this right side term, you are doing integration with respect to f, and you are differentiating with respect to t. Now it looks like for the timing you keep this integral aside. Now you apply this differentiation. It looks like u integral v plus integral v into derivative of u. So since it is in frequency, so we'll have only one differentiation term you'll get. When you do that, I can write this as the right side term. I can write it as, since if you differentiate it, u into derivative of v plus v into derivative of u. So u is g of f, v is e power j 2 pi f t. As you're doing differentiation with respect to t, so you treat the rest of the term as constant. Other than t, you treat it as constant. So it looks like e power j theta. You can write it as j e power theta. So I can write, when you differentiate it, I can write this as j 2 pi f into e power j 2 pi f t into g of f. So this is what the first term is when you do the differentiation for this. Now if you do the second differentiation, second term, that is v into derivative of u. When you take derivative of u, since it is in frequency, as you are doing the differentiation with respect to time, so it becomes 0. So no need to write that. Then we have this integration as it is. You can write that integration integral minus infinity to plus infinity df. Now please try to understand. For the time being, I'm keeping this aside and I'm applying this differentiation to these two terms. Then I'm going to write it like this. Now you readjust this. When you readjust this, then you can write this as, I'm taking j 2 pi f outside, j 2 pi f You know why I have written j2 pi? Since I am differentiating with respect to t, so you treat this rest of the term as constant. So you can write integral minus infinity to plus infinity g of f into e power j2 j2 pi f t df. Now please see this term. This term, this term, I can write it as f inverse of g of f. This term I can write it as f inverse of g of f. So what I'll do is I'm taking this f inverse to the other side. Then it becomes the Fourier transform of d by dt of g of t, which is j2 pi f into g of f. This is how you are going to get the first differentiation. Now, suppose if you do the same problem n number of times, like this, what you have to do, you have to take second differentiation again, you have to take third differentiation, fourth differentiation, like that, nth differentiation. In general, you can write, the Fourier transform of d power n by dt power n, the nth derivative of g of t, which is nothing but j2 pi f whole to the power of n into g of f. This is how you are going to get the nth derivative of it. Now you may ask how you can prove this. Just observe it. This is the first differentiation. Again, you differentiate this. Then when you differentiate it again, you will get the same term. Again, j2 pi f will multiply here. So that means if you differentiate twice, you will get j2 pi f whole square. Like that, if you differentiate n times, you will get j2 pi f whole to the power of n. So this is now what the differentiation in time domain property is. Is it clear? Now please post it in the chat box. Now please post it in the chat box. Is the concept clear now? Yeah, right. Now you may ask a doubt here. Now you may ask, what is the use of this property? Now let us see this. You can I'll show with some waveforms. Now just I am drawing some waveform like this. Now I'm going to draw some waveform like this. Now observe it. Here I have drawn one waveform, which is a triangular waveform. Now I have drawn another waveform, which is a pulse, a rectangular pulse, and I am going to draw another waveform. Now observe these three waveforms. Now assume that this is 0 and all are in time domain only, and it is existing on, and this waveform is existing from minus t by 2 to t by 2, and it is having an amplitude of a. Let us assume it like this: a 0 minus t by 2 to t by 2, and here the amplitude is a. The amplitude is a, and it is existing at minus t by 2, and it is 0, and this is t by 2. Here the amplitude of this pulses is a. Now can you give me the, is there any relation between these three waveforms? Can you observe, can you find any relations between these three waveforms? Please post it in the chat box. I have drawn three waveforms. One is a triangular waveform, one is the other one is a rectangular pulse, and the third one is an impulse signal at minus t by 2 and t by 2. Is there any relation between that? Yeah, Jyoti, you are saying that yes. Can you tell me that what is that relation? If you observe it carefully, you can write a mathematical equation to this, right? Now tell me what should be the mathematical equation for a waveform which is existing from minus t by 2 to t by 2 with an amplitude of a. What should be the equation? You please tell me. Already we discussed an example. Some of you please unmute yourself and tell me. Already assume that this is x of t and this is y of t and this is z of t. I'm taking three different waveforms to represent. I use the notation x, y, z. But there is a relation between x, y, z. We'll see that. What is that relation we have? Now, please tell me. Already we have solved such type of examples in the previous classes. Now, please tell me the relation for a triangular pulse, triangular waveform, whose amplitude is uh, minus t by 2 to t by 2 with an amplitude of a. Now, this you can write in coordinate system like this. The coordinates for this is minus t by 2 comma 0 and the coordinates for this is 0 comma a. Yeah, x of t equal to, no, I think you are wrong. Upraya, you just please check it, Amma. This is not x of t. So you have to write in the place of x, you have to write this amplitude. Please see. Here I need to write an equation of a line first, this segment. You please assume this segment as AB and this segment as BC. Now you need to write the equation of a line AB, which is nothing but y minus y1 into x minus x1. Using that relation, you need to find it. Now first tell me the equation for this line. The equation for this line is, I need to use this formula, y minus y1 equal to y2 minus y1 by x2 minus x1 into x minus x1. This is how what the generalized equation. But for our problem, our x is t and our y is a. Sorry, our y is x of t. Now I can write x of t minus y1 is 0. If I assume this was x1, y1, the coordinates are, this is x1 and this is y1, and the coordinates here are x2, y2. So I can write y1 is 0. So y2 minus y1, I can write it as a, x of t equal to a by x2 minus x1. So when you consider x2, it is 0, minus x1, it is minus t by 2. So minus and minus becomes plus. So it is t by 2. So I can write this as t by 2 into, now x. My x is, I have elements on the x-axis which is small t. I can write it as small t minus x1. So my x1 is this one, which is minus t by 2. Minus and minus becomes plus t by 2. So from this I can write the relation is 2a by capital T into t plus t by 2 is the equation of the line, between minus t by 2 less than or equal to t less than or equal to 0. That means this part of the waveform portion, I can write the waveform like this. Similarly, for BC also you need to write. Now here already I have x2, y2. Uh, I can assume the coordinate at C as t by 2 comma 0. So my x1, y1 now is t by 2 comma 0. Now again I need to use the same condition. So y1 is again 0. So I can write y2 minus y1, which is you'll get minus 2a by t. Since x2 minus x1, my x1 is minus t by 2. So I can write minus 2a by 2 into x minus x1, I can write minus t by 2. So this is what the equation I'll get from t by 2, sorry, from this I can write from 0 less than or equal to t less than or equal to capital T by 2. Now please try to understand the relation for, this is what the relation for x of t. Now, if you rearrange this equation for x of t, I can write this equation for x of t, which is 2a by t into t plus, now this 2 and this 2 gets cancelled and tt gets cancelled. So you will get plus a plus capital A, which is minus t by 2 less than t less than 0. This is what the equation for the line. And another equation is minus 2a t by capital T. And now this minus and this minus becomes plus, and 2 gets cancelled and tt gets cancelled. So you will get plus a. This is what the relation for 0 less than t less than capital T by 2. Now, please try to understand. This is what the equation for x of t for a triangular waveform. Now what I'll ask you is, now you differentiate this. When you differentiate it, then you will get d. Now, then I can write it as d by dt of x of t. When you differentiate this, when you differentiate this, now please try to understand. I'm using some other color for your understanding purpose. Now when you differentiate it, now what will happen? If you differentiate the same equation, if you differentiate this equation, then I can write this term as d by dt of x of t I need to find. When you differentiate it, since a differentiation of constant is 0, this term gets cancelled. Now when you differentiate it, so you will get 2a by t, you will get 2a by capital T, which is from minus t by 2 to t less than 0, and minus 2a by t 0 less than t less than t by 2. This is what the differentiation of your, this is what your x of t is. So when you differentiate this x of t, you will get this term like this, only 2a by t, which is a constant. Now please see the waveform y of t. Now after this y of t, you will get minus t by 2 to 0. The amplitude is 2a by t. So that means here the amplitude is rising. The amplitude is rising to a peak value from 0 to in the upward direction. In the upward direction. That's the reason you will get positive 2a by t. Then, and it will continue, the same amplitude will continue up to 0. That means it maintains the same amplitude. And from 0 to t by 2 also, it is 2a by t again. That means the same amplitude will continue, and at t, it is again minus, so it is falling. So that means this differentiation of x of t is nothing but your y of t. So I can write this as your y of t is nothing but d by dt of your x of t. Is it clear up to now? జాగ్రత్తగా అర్థం చేసుకోండి అమ్మా. నేను ఇక్కడ 3 వేవ్ ఫామ్లు రాసి ఈ వేవ్ ఫామ్ కి y of t కి x of t కి రిలేషన్ చూపించాను చూడండి. Your y of t is nothing but d by dt of x of t. Is it clear? Please post it in the chat box. నేను ఎక్స్ప్లెయిన్ చేసిన అర్థమైందో లేదో ఒకసారి చాట్ బాక్స్ లో పోస్ట్ చేయండి అమ్మా. అర్థం కాకపోతే ఒకసారి మళ్ళీ ఎక్స్ప్లెయిన్ చేస్తానమ్మా. ప్లీజ్ పోస్ట్ ఇట్ ఇన్ ద చాట్ బాక్స్. మా ఏదైనా డౌట్ ఉందా ఇక్కడ దాకా చెప్పిన టాపిక్? ప్లీజ్ పోస్ట్ ఇట్ ఇన్ ద చాట్ బాక్స్ ఆర్ అన్మ్యూట్ యువర్ సెల్ఫ్ అండ్ tell me. Is it clear up to now? That means if I have a triangular waveform, yeah, Jyoti, yes, you repeat that. Yeah, just observe it, Amma. I'll repeat it once again for your convenience. Now, first see, I consider 3 waveforms, and all these 3 waveforms are existing from minus t by 2 to t by 2, and with an amplitude of a. So the first waveform, oh, second one. Okay. Now, see the second one. So here I have drawn a rectangular pulse of amplitude A, and it is existing from minus t by 2 to t by 2. Now, observe this. This is what the equation for x of t. That means this is nothing but the equation of a triangular waveform. This waveform. ఈ waveform యొక్క ఈక్వేషన్ నేను ఇక్కడ డిరైవ్ చేశానమ్మా. This is what the equation of a triangular waveform, and x of t is existing is 2at by capital T plus a, which is existing from minus t to 0, and minus 2at by t plus a, which is existing from 0 to t by 2. Now what I am doing is, I have my x of t. Now I am differentiating this x of t with respect to t. That I have written it as d by dt of x of t. ఉన్న x of t ని టైం తో డిఫరెన్షియేట్ చేస్తున్నాను. When you differentiate it, ఈ ఈక్వేషన్ లో ఏమవుతుంది చూడండి. Here a is a constant, as you know. Differentiation of a constant is 0. This is not required. This a. Now, if you observe this part, as you are differentiating with respect to t, you will get 2a by capital T. Here, as you are differentiating with respect to small t, you are going to get minus 2a by t. So when you differentiate x of t, you are going to get 2a by t for minus t by 2 to less than t less than 0, and minus 2a by t 0 less than t less than t by 2. This is what the differentiation of x of t you will get. Now observe this equation. When you observe it, if I ask you to plot the waveform, if you see what is the magnitude of this d by dt of x of t, tell me. When I ask you the magnitude part, if you see the magnitude part of this, the magnitude of d by dt of x of t, which is nothing but 2a by capital T, right? Which is nothing but this I can write it as a by t by 2. Can I write it like this or not? This I can write it as a by t by 2. Now please try to understand. So what you will get at t by 2, you are going to have a signal which is having an amplitude of capital A, and it is continuing up to 0, and it will extend, and at t by 2 the amplitude is minus. So you see the difference between plus and minus. Plus in the sense it is rising. So observe it. from minus t at minus t by 2, the amplitude is at minus t by 2, the amplitude is a by t, a. That means it starts from 0 and it goes on increasing to a maximum value of a, and it will continue up to t by 2. Now at t by 2, what will happen? The amplitude is falling to minus a by 2. So it is falling from maximum value to 0. So this is what a rectangular waveform is. So that means this equation is nothing but the differentiation of x of t is nothing but your y of t. Please try to understand. Already I have drawn a y of t waveform. So to get this y of t, just you need to differentiate this. You will get this y of t. Is it clear now? Please post it in the chat box. Jyoti, is it clear, Amma? Yeah. Now what I'll do is, what I'm going to do is, I am going to consider my y of t. Again, I'm going to differentiate this y of t. Now please pay attention and try to understand the logic. When you see this y of t, what will happen? Y of t, you'll have a rectangular pulse, which is now just I'm going to draw this for your understanding purpose. So I'm going to use red color. What will happen? It starts with 0 and it goes on increasing, and it maintains and it maintains a constant value, and from there it falls again. So please try to understand at minus t by 2 how the amplitude is for this rectangular pulse. Please observe it. It starts varying from 0 and reaches a maximum value at minus t by 2. Am I right or not? Please see the waveform and tell me. At minus t by 2, the rectangular pulse starts at 0 and it goes on increasing from 0 to it reaches a maximum value a. And once it reaches the maximum value, it maintains the same value up to t by 2. Once it reaches t by 2, what will happen? It starts falling from the maximum value to 0. That means where you can find the variation? You can find the variation only at minus t by 2 and t by 2. Is it clear? Please try to understand. Please observe it, observe the waveform and post it in the chart box. Is it clear how this rectangular pulse is varying at minus t by 2? The amplitude is varying from 0 to a maximum value, and it maintains the same value up to t by 2. And once after reaching this t by 2, it falls from a maximum value to a lower value. Is it clear? Yeah, Nikita, right. Now, when you are differentiating this y of t, what will happen? Here the amplitude is changing. Here the amplitude is changing with respect to time. So these two will not affect since it is varying. But here the amplitude remains constant. So when you differentiate here the amplitude is constant. When you differentiate a constant, what you will get? You will get 0. So if you differentiate this y of t, you will get z of t. So my z of t is nothing but d by dt of y of t. Now please try to understand. Now when you see this differentiation of y of t, you differentiate it. At this place the amplitude is varying, and at this place the amplitude is varying. In between that the amplitude remains constant. So you don't have the waveform in between minus t by 2 to t by 2. But at minus t by 2 and at t by 2 you have the amplitude which is varying, which is a. At minus t by 2 it starts from 0 to a maximum value, and here also it reaches from a maximum value to a minimum value, so that I can draw the directions. In this case I can draw the direction which is in the upward direction. In this case I can draw the waveform which is in the downward direction. So now observe it. To get this x of t, y of t, z of t, what is the thing that is common? The common thing is your x of t. So I can write the relation for x of t. So here I am going to write my x of t my x of t is a triangular waveform. If you differentiate x of t, d by dt of x of t, you will get a square or a rectangular pulse. Again, if you differentiate this x of t, then I can differentiate it once again. Then I can write it as d square by dt square of x of t. Then I'll get an impulse function. Now please see this. If I know the triangular waveform, if I ask you to find the Fourier transform of a square waveform, just you differentiate the Fourier transform of this, then automatically you can find the Fourier transform of square waveform. That is how you can use this differentiation in time domain property to solve the problems. I hope is it clear to all of you? Please post it in the chat box. So the same triangular pulse, if you differentiate once, you'll get square waveform. Again, if you differentiate the triangular pulse, you'll get impulse waveform. So I can say that if I ask you to find the Fourier transform of an impulse function from a triangular waveform, you differentiate the triangular pulse twice, you'll get it. So that is how you can use this differentiation in time domain property to solve the problem. Now see this example, you will understand it. Now see this, this is what the differentiation in time domain property. Now when you already I have read the proof also, you will understand now. Now you can understand all this. Now observe it. Just observe it. Here I have drawn a unit step function g1 of t. So I can say that the g1 of t I can write by a mathematical equation which is u of t, which is equal to 1, which is a unit step function, which is 1 and it is existing from 0 to infinity. Now, if I differentiate this unit step function, you will get an impulse function, which you already know. That means you will get an impulse function only at t equal to 0. This is constant. Differentiation of a constant is 0 again. So you will get an impulse function only at t equal to 0. So that means I want to find the Fourier transform of an impulse function from a unit step function. So try to understand, if you differentiate the time unit step function, you will get an impulse function. So first you need to know what is the Fourier transform of u of t. The Fourier transform of u of t is 1 by j2 pi f. Please try to understand. The Fourier transform of u of t is 1 by j2 pi f. So if we apply the differentiation in time domain property, so I can multiply j2 pi f into g of f. My g of f is this one. So j2 pi f gets cancelled, you get impulse function which is 1. Is it clear? Is this example clear, or shall I explain? Shall I solve this in the chart board, Jamboard? Please post it in the chart box. Is this example clear to all of you? ఈ ఎగ్జాంపుల్ అర్థమైందా లేదమ్మా? ఇక్కడ నీ డిఫరెన్షియేషన్ ఇన్ టైం డొమైన్ ప్రాపర్టీ ఎలా అప్లై చేస్తాను చూడండి. సో వెన్ యూ అప్లై దిస్ డిఫరెన్షియేషన్ ఇన్ టైం డొమైన్, ఫస్ట్ ఫోరియర్ ట్రాన్స్ఫార్మ్ మనం అడిగింది ఇంపల్స్ ఫంక్షన్. ఇంపల్స్ ఫంక్షన్ ఫోరియర్ ట్రాన్స్ఫార్మ్ అప్లై చేయాలి అంటే you need to differentiate the unit step function. But when you write the formula, జాగ్రత్తగా గమనించండి. I am going to use this example in the Jamboard. Now just see this example, and with this example I'm going to stop for today's class. First see, now as you know that the property of differentiation in time domain property, when I write the differentiation in time domain property, I can write the Fourier transform of d by dt of g of t is j2 pi f into g of f. Here g of f is the Fourier transform of this g of t. G of f is the Fourier transform of g of t. Whatever g of t we have. Now, for the given problem, he has asked us to find the Fourier transform of an impulse function from a unit step function. From a unit step function. Already has given the unit step function. Now, first you should write the relation between unit step function and impulse function. When you plot the unit step function, it looks like this. This is what the unit step function is. It is 0, the amplitude is 1, and this is what u of t is. So I can write by a mathematical equation u of t equal to 1, 0 less than t less than infinity, and 0 elsewhere. This is what the relation I can write. Now, suppose if I differentiate this unit step function, what will happen? See, observe it at 0, the amplitude is varying from 0 to a maximum value 1. And once it reaches the maximum value 1, and from there it maintains the same value throughout. So that means if you observe this, once it reaches the maximum value, it is maintaining the same value. That which means that the amplitude is not varying. When you differentiate it remains constant, right? What is the differentiation of a constant? The differentiation of a constant is 0. So when you differentiate this unit step function, you will get a waveform. Like this, which is varying from 0 to 1. This I can write the relation. This I can represent it as del of t. That means from the unit step function, I'll get the del of t by differentiating this unit step function. So I can write a relation d by dt of u of t, which is nothing but del of t. So now what he has asked us to find, he has asked us to find the Fourier transform of this. So you apply Fourier transform on both sides. When you apply Fourier transform on both sides, you will get Fourier transform of d by dt of u of t, which is equal to the Fourier transform of del of t. He has asked us to find the Fourier transform of an impulse function. As you know, the Fourier transform of an impulse function is 1. Now we'll see whether you get the Fourier transform of an impulse function is 1 or not. Now, first you should find the Fourier transform of u of t. Now, first you need to find this. I can treat it as g of t. According to the property d by dt of g of t, the Fourier transform of d by dt of g of t I can write as j2 pi f into g of f. So g of t is nothing but the Fourier transform of g of f. So first I need to find the Fourier transform of u of t. So first I need to find the Fourier transform of u of t. When you find the Fourier transform of u of t, which you already discussed in the previous classes, the Fourier transform of this is nothing but j omega you are going to get, or j2 pi f you will get. Sorry. So you are going to get 1 by j2 pi f you are going to get. You are going to get 1 by j2 pi f. Now, from this property, I can write in the place of g of f, I can write the Fourier transform of u of t. So which is nothing but 1 by j2 pi f. This j2 pi f and this j2 pi f gets cancelled, so that I will get 1. So then now I am going to write the Fourier transform of d by dt of u of t, which is nothing but j2 pi f into g of f. But my g of f is nothing but 1 by j2 pi f for the unit step function. So I can write 1 by j2 pi f. So this gets cancelled. You are going to get 1. This is what the Fourier transform of d by dt of u of t, which is nothing but the Fourier transform of an impulse function. Is it clear? Please post it in the chat box. Is this concept clear to all of you? Please post it in the chat box. That is how you can find the Fourier transform of a unit step function. Is it clear?